Well, I mean, okay.
That's fine.
Okay, shall we get started? So I'm very glad to welcome Nikolai here. He is co-supervising our project on using deep learning for the cloud tracking. We're running with Dinesh at the moment, and I'll leave the floor directly to you.
Thank you very much, Jan. So, I'm a PhD student at Mark Polyphase group at ETH Zurich. We work on computer vision and geometry. And before I actually start with my talk today, I would like to introduce all the wonderful people I've been working with on this project. So it's Lubor Ledicki, who actually proposed the idea I'm going to talk about. Torsa and Mark gave lots of useful feedback, and Akihito was my closest collaborator on the project, so I'm very thankful to them. So the talk is going to be about a novel machine learning technique, which basically helps you to give a compressed representation of the data. So it will be done in an unsupervised manner, and the goal will be to demonstrate it for interest point detection in images, but it's probably an extendable technique to other domains as well. So first of all, what is the interest point detection? This task was studied for quite a while in the computer vision community, and the goal is the following. You have a pair of images and assume that the camera moved between taking them. For example, this left image was taken from this position, and the right image was taken from this position. Now you don't know how the camera moved, so you'd like to estimate this transformation. But how you do it? So basically you detect some key points in the left image and in the right image, and then based on those key points you will estimate how it was transformed. Just for me to get a better understanding of the audience, can anyone who worked with interest point detection raise their hands, please?
Very clear.
No one, so this. Okay, so I'll try to make it as high level as possible, like give a general idea. So when you detect the point, you basically want to redetect the corresponding point in the right image. So it's not like you detect some random points in the left and in the right image. You want to detect corresponding points. As an example, look at this point, for example. It's right here. So in the right image, the correspondence was detected with the same scale. So basically, the radius of the circle shows the scale at which it is detected. So that's your goal. You want to redetect the same features because it will help you later on when you estimate the transformation. Oh, as I said, this is like a well-studied task. There was like 20 years of research on it, and there are some well-working solutions like DOG feature detector.
And is the task to find corresponding points in both already, or is it just finding points which would be suitable to be redetected on the other image? Is it single picture, or is it already the combination of the two pictures?
You strive for it to be redetectable later on.
Okay, that's on the single image.
But it's single image, yeah.
Yes.
But you want them to be unique enough
okay.
to kind of redetect them later.
So you don't know whether you're going to find them.
Yes.
Yes, exactly. You strive for the best, and then you see how it goes. But that is the basic task. Well, there are also some other tasks where you want to detect interest points. So one such task is interest point detection between different image modalities. So for example, you see the left image is an RGB frame, and then the right image you see a depth image. So depth image is basically, you take it from the depth camera, like Kinect, and it basically measures the closest distance to the point you see. Clearly that is a complicated task. You want to redetect the same points here and there, although in the right image there's no texture, right? So whatever simple heuristic you pick, it's not going to work that easily, because if you, for example, pick some blobs in the left image because of the texture on the walls, it's not necessarily present in the right image because it's a different modality, distance to the object. So this is a very hard task, and there's no, to me, it's not known. There's no known solution. I looked through the literature. People mentioned, yes, there's this problem. We don't know how to solve it, so we just try out, whatever detectors we have, and see how they work. But it's not something which is solved. So what is more interesting is that for some unexpected tasks, it is also possible to formulate interest point detection. For example, you could be working with the videos, and you would like to compress the video somehow. So you select some interest frames. Why would you do that? Because there are some tasks like copyright infringement detection, which are solved by Google. So somebody uploads the video, but you don't want to store the whole video or duplicate it for some particular task. You want to store some concise representation so that when another video is uploaded, you can quickly match them. So this kind of technique could also be useful, but there's no general method to learn such interest point detection. So this is what this work is trying to solve. So our goal is to really have some learning-based interest point detector, and for that we formulate some special kind of laws. So here I just want to summarize the key idea. It is illustrated on just simple RGB interest point detection, but it is extendable to more complicated cases, and later I will show how it is. Now, so what is the idea? Basically, you want to provide some real valued response to every pixel of the image. So you see the pair of images on the left. It undergoes some perspective transformation as when you move the camera. And on the right, you actually see the responses which I was talking about. So basically your function assigns some response to every pixel in the left image and in the right image. And the idea is that if you look at the extrema of this response across the image, for example, you see here basically the color means the value encoding. So blue means negative, larger negative, and red means larger positive. So you see that this dark blue, this eye of the animal, it is actually blue in the right image as well. So you want to have this assignment to each pixel to be reproducible in the sense that extrema of this assignment are also reproducible. So this will be formulated as a ranking problem. So you basically want to rank all the pixels in the left image and in the right image such that extrema map to each other. But if you already have a ranking which is preserved, like if one point in the ranking here is larger than this one, for example, then it is also larger in the right image. If this is satisfied, then the extrema of the function also map from the left image to the right image. Now,
but sorry, when you do the mapping, obviously the position of the pixel or the identity of the pixel might change, right? Because you have changed things. How do you intend them to make sure you're not just randomly mapping a maximum of another maximum that's on the other image? Do you consider that somehow?
Oh, sure, yeah. Right, that's a good question. So the point is that you need to know the correspondences. So you need to know which points in the left image correspond to the points in the right image. How would you do that? For example, you could simulate the perspective transformation as just transform the image randomly, and then you have this example. You know the correspondence because you actually mapped it with some metrics. Another option is that you actually have a 3D model so that you can project points to both images, and then you know what is the correspondence. And yet another option is Kinect RGB frames. Basically, Kinect consists of two cameras. One is RGB and another one is depth. But the cameras are calibrated, meaning that you know how they are located with respect to each other. So you already know the transformation in advance, and you can use this later. So this is, did I answer your question?
Yeah, I see. So you assume you know which pixels correspond to which pixels?
Yes. So this is the key thing to understand that.
But what I'm wondering is when you change, you might have some pixels that are lost and some pixels that have appeared new because of the.
That is possible, but basically that gives you the best. You're doing the best that you can. If there are some new pixels which appear, you can't really do anything. So you only care about the pixels which are present in both images. So you enforce this ranking constraint between those visible pixels. Now, this was just the demonstration of the idea. And now how are we actually going to do that? I mentioned this function which we assign to each pixel, but what is this function? So basically, we'll call this function h, and it will depend on two arguments. So one is p. P actually represents the point in the image, and the point, it's just not enough to give the color of the pixel. You should give something like a patch around this point, otherwise there's not enough information. And w is the vector of parameters. So h will basically, it could be anything. In this work, we used a neural network. So it should be a differentiable function of the parameters w. And you want to learn those w parameters. So this is how we represent the ranking. The higher the h function, the higher the rank is. Now, how do we encode this ranking preservation condition? So again, what did I mean? So if this point is ranked higher than this point in the left image, we want that the corresponding point here, and that's where correspondence is come into play, is ranked higher than this point in the image. So it's based on two pairs of corresponding points. Now, this condition can be represented as written here. So what's written in the first row? So if so P is basically the point, or the patch which represents the point. T is basically the left image, and TD means the right image. So it's transformation applied to the image, like a perspective transformation. And I and J are the positions in the image. So that's the as I said, for example, this could be I, and it's also I in the right image, and this could be J. Now, the first row is basically says that if it is I is more than J in the left image, like those two positions in the image, then I is more than J in the right image. And this is basically the other way around. So you need to take into account both conditions because both are possible. So it's a logical OR condition between them. Yes?
I still have a question regarding the transformation. Here it looks like you're trying to learn H somehow.
Yes.
Do you also learn T?
No. T is basically, you sample T to get it robust to some kind of transformations. But you don't learn it.
You know it.
Yeah,
Yes.
but then I'm missing a little bit the overall goal, maybe, because I thought that you wanted to find what is T. So what is the transformation between the two images?
Sure, yes. You know it in the learning time, you don't know it in the test time. But in the test time, you're not trying to enforce this condition. You expect that it is enforced in the training time.
Okay.
So you expect that it will hold. Did I answer your question? So now, but this is a logical condition with some function which we want to learn. It doesn't look any differentiable, So how do we actually learn it? What's the algorithm to get to such h function to w parameters? So here's how we do it. So we basically introduce new R function which represents the ranking preservation, this ranking agreement. So we want this function to be positive when we are good. So when the ranking is preserved. So how do we do it? Basically, we take this difference between I and J in the left image, and the difference in the transformed image as well. So you see if this one is larger than this one, and this one is larger than this one, then it's positive, and the other way around as well. So basically, it will be positive. That's what we want. Now, this is still not good enough because okay, that's another logical condition, but how do we optimize it? So we introduce this function. It's called hinge loss, I guess. Maybe you know this. So this is basically a function which is maximum of 0 and 1 minus r. And if you minimize this function, then you will be striving for this condition. So this is the goal here. So it's not only that we optimize for it to be more than 0, we actually optimize it to have some kind of margin from 0. So we want it to be to have some distance from 0. The reason for that is because, simply if it is 0, then it doesn't satisfy the condition you want, because you can just take a constant everywhere. So that's a very bad solution. So we want to have it more than 0, and we want to keep far from this dangerous constant solution. That's why we want some margin. And this is what this hinge loss is doing. So this hinge loss is kind of used in other machine learning tasks, for example in SVM. And SVM does exactly that. It enforces some kind of margin between the separating hyperplane and the points. Yeah, maybe are there any questions so far? Do you see the concept?
So why you don't just maximize R?
Exactly. That's my question.
I mean,
Well-
you have now these more complicated objectives.
Well, we try to maximize R actually, that makes sense, but unfortunately it's unbounded.
Okay.
So yeah, it would be enough to have some 2 points infinitely large, infinitely far from each other, and then it will
So you
watch
do
up.
something like a norm, you change the norm here, that you enforce it over every pixel or something, or you try to maximize the minimum of R, for example.
Oh well, optimizing. So here is the sum is optimized, but yes, one option would be to take a different norm, but that's kind of, it's very hard to optimize. If you take, for example, maximum of some function, then if you optimize it with gradient descent, there will be only one active branch all the time, and then the optimization will be very slow. So it's complicated. So
Isn't this also a challenge, because this is a bit also not smooth, no? This maximum.
yeah, it's not only non-smooth, I will say more, it's not convex, because simply if you look at this function, it's non-convex already.
Sure, yeah, it's a binary.
So yeah, it's a challenging optimization, but we hope that neural networks also deal with non-convex optimization. They still work. So the hope here is that our methods could still deal with that. So here, yeah, as I said, so we basically take this hinge loss on top of R, and then we basically sum up over all the available images and over all the available transformations and the correspondences. So this is a huge function. During the training time, we just sample some like Monte Carlo sampling, sample points from there and learn them, like stochastic gradient descent.
And you have a huge data set of these correspondences, samples with correspondences. I mean, somebody has to give you this. Somebody has sat there and said this point corresponds to that one, or do you construct them just by a transformation?
So that's a very good question. So we tried all the 3 scenarios which I mentioned. So one scenario was to take a GTU robot arm dataset. So basically they have a database of images where the robotic arm was taking pictures around some objects. Another scenario which we tried was, and there you basically, there was also a scanner, so they had a 3D model, they had exact positions of the cameras, so they could, we could project the points and get the correspondences. One other scenario is we also try to artificially warp images to simulate it, as I said before, and that also works. Maybe a bit worse than having the exact, the correspondence from 3D. And the third scenario was for Kinect. You actually just know it, because that's a property of the 3D. If you know the kind of color in the depth channel, you actually know the 3D point. So you can project it on RGB. So it just comes naturally.
I thought the question was more about ground truth or like validation. Did I miss it?
No, I mean, where you get the data from. I mean, you need
The training data.
the training data, right?
Yes. About the validation, we'll talk a bit later. I'm still explaining how the training works. So, okay, thanks. So this is how the training goes. So, so these are those two pairs of correspondences which I was talking about. You can figure out which is which. So basically, this one corresponds to this one, and this one corresponds to this one. This is the H function. Please notice that this H function basically shares W parameters between all the branches, so it's exactly the same H function. Then you subtract it, as I was explaining before, multiply, take hinge loss, and you can actually calculate this loss function, which I mentioned before, for just this quadruple of patches. So that's why we actually call it quad networks. That's the name of the method, because it works on the quadruples of patches or some other objects. I would like to pause a bit. So this is the pipeline. So basically, you can calculate the loss, and you can already do the stochastic gradient descent update based on this one example, basically this one quadruple. But what I would like to mention is that it's quite an unusual, because I've never seen any method in machine learning which works on quadruples of patches, like let's say there are some methods which use 4 of something, but this 4 is not kind of uniform. They're typically different entities or something. And this is amazing, because so basically machine learning methods can be divided into a few groups. So one group is you just use one page like image for learning, one object. So that's a classification. You assign label cat or dog, for example, to the image. There are some methods which work on pairs of images. So, for example, they want to say that something should match to something. Like there's a depth matching task which is also done with deep learning, like stereo matching, where you search for correspondence in another image along the line. And then you want to say that some patches match to each other and some patches don't. Then you work on pairs of patches. There are some methods which work on triplets of patches, which try to do some embedding. So for example, they want to embed a picture of a human face into some manifold. And then they say that the face of the same man taken at a different angle should be closer on the manifold than like face of a different man. So this takes 3 patches, because there is let's say left image of this man, left image of right image of this man, and just another image of another man. So this triplet. But this is 4 pages, and the method is unsupervised in the sense that you don't give a solution to this ranking. So this unsupervised ranking was not done before in the literature. So now about the results. So for standard RGB detection, so basically you just have 2 images from the same domain. That's the simplest case. So we get something which looks like DOG. So DOG is a well-known method for doing that. And we got something similar, so it's a radial symmetric gradient-like function. So you can see a bunch of numbers in a paper for repeatability metric. I don't put it there, it's too large. But basically, the impression is that you get something which is very similar to DOG, so probably DOG is actually a very good method. Now, where you can actually see the advantage is this complicated cross-modal task, where you take RGB image and the depth image from Kinect, and you actually want to redetect the same points. So basically, I'm not sure how visible it is, but the yellow curve is actually our method, and you can actually see that there is an advantage of all the other methods, including DOG. So here's a bunch of filters which so this was done with a deep neural network. From a deep neural network, you can extract the filters at least for the very first layer and see how they look like. So this was something like 7 by 7 filters. I'm not sure what you can actually see here because they are kind of low resolution. But I think, in my opinion, I see that there are some high frequency components here. There are some blob-like components like this one, and there's also some edge-like components like this one. Although they look kind of blurry, but you can actually see that the network learned something which is different from just a simple radial symmetric function. Yeah, there are also some, I guess, bunch of numbers in the paper. So this is it for now, and I would be happy to take some questions for you on this technique.